Hello, I'm Jacopo Pinzino, and I will speak about the physics beyond standard model with CAN at N62. N62 is a high-precision fixed-target Cloud experiment at CERN SPS. Its main goal is the measurement of the branch duration of decay plus in plus neutrino. But they have even a broader physics program with electron flavor and number evaluation in CAN decay. About that, I will speak after the K plus in plus neutrino, and a needed set of particle searches. This experiment started in 2008 with approval. Then, after some years of pilot and commission run, started the first real run in 2016 that was in continuous data taking until the end of 2018. Data taking will be resumed in 2021 after some improvements. This decay is highly sensitive to new physics. It's a flavor change in network current process will be that 3 level, highly CKM suppressed. It's very clear theoretically due to the short distance contributor and to the fact that the hadronic matrix element can be extracted from precise measurement of the branch duration of the K plus in path 0 A plus neutrino. The model prediction, as you see, are really good in precision. Indeed, the K plus in pi plus neutrino have a branch duration for the standard model of 9.3 plus minus 0.8 times 10 to the minus 11. The natural decay have a prediction of 3.7 plus minus 0.7 times 10 to the minus 11. And up to now, before NCSU and before COTO, the experimental result were that of the experiment E787 plus the upgrade E949 for the charging one with a branch ratio of 17, measurement of 17 times 20.3 plus 11.5 minus 10.5 times 10 to the minus 11, and for the natural one, an upper limit of 2.6 times 10 to the minus 8. This dash to decay, the charge and the natural one, can discriminate even among different physics scenarios. In this histogram, you can see the standard model prediction here, and the prediction using other models, like models with CKM, like flavor extractor, coastal random syndrome, simplified Z and Z paired model, little with T-parity models, lepton flavor universality model, leptoporks, meaning supersymmetry models, and so on. Here you can see the web position of the result of the previous experiment E787 and the upgrade E949 with 1 sigma, and then the superimposition of the result presented here from NCSU that you see have a better resolution. The charge decay, the K plus of pi plus neutrino, together with the B plus of Kester plus neutrino can probe even the lepton flavor universality. Indeed, an iteration responsible of the lepton flavor universality evaluation can copy mainly with the third generation of left-handed fermions. The K plus in pi plus neutrino is the only Cannon decay with third generation of lepton, the neutrino in the final state. And the deviation from the standard model of this decay together can be closely correlated to the similar effect in the measurement of the decay of B in K star plus neutrino, as in the plots showed here on the right. And here you can find even an article that explains better these models. Speaking about first about the NCSU layout, we have a primary proton beam arriving from the SPS with 400 GeV of proton that hit the target and generate a secondary positive beam of 75 GeV. It's not separated, so we have 70% of P plus, 24% of proton, and 6% of kaon. So we have to identify the kaon inside this beam. We use for that the K-tag, that is a differential Cherenkov detector to identify the kaon. Then we have beam trackers done with 3 stations of silicon pixel to identify direction and moment of the cone. Then after that we have a charger veto for the interaction of the beam with the GTK. We have the decay region, 65 meters of the 60 meters sorry, of the decay region from 105 and 165. We have a spectrometer with a dipole magnet here to identify momentum and direction of the pion. We have the reach to a ring imaging channel to identify the pion to separate it from muon. And then we have a system of photon veto lab that are the large angle. They have calorimeter electromagnetic, calorimeter LKR with liquid krypton, RC and SAC so to veto photons. We have a system to veto muon that is a hadronic calorimeter MAV1 and MAV2, and other system always to veto particle to trigger the events. The main important part of the strategy is that we use a new technique of decay flight, respect to the previous experiment that was using the decay of cone at rest. The signal is very simple for this decay: one beam track and one charged track downstream, and nothing else. The background are all the decay modes and the beam activity. We use the cinematic to reduce the background, so we measure the missing mass of cone minus pion. Here you can see an histogram plots of the missing mass of all the main decay of background and of the signal decay enhanced of a factor 10 to the 11. Otherwise, it would be impossible to see in this plot the signal. We separated the signal in two regions, one between the area of the background that came in mu neutrino and the peak of π+π0, and the second region is between the peak of the π+π0 and the triply area. Together with that, we select the momentum of the pion between 15 and 45 GeV, fiduciary decay region 60 meters as before. Then we use, after the precise cinematic reconstruction, a particle identification. We told the detector that I told you before, hermetic photon detection and sub-nanosecond time. Indeed, the timing between the subdetector and 100 picosecond will reach 10 to the 4 of the background suppression from the cinematic and 10 to the 7 suppression from mu identification and π0 identification. Then we use a blind analysis for signal background and multivariate analysis for the particle identification upstream background reaction. Here you can see an histogram of missing mass versus moment of the pion. You can see the main background, for example, here the K plus in mu plus neutrino, here the peak of π+π0 and the area of 3 pion. Here is the first region of the signal between 15 and 35 GeV, and upper there is the second region of signal that is from 15 to 45. Up to 2017, the region, even the second region, was between 15 to 35. Now it's up to 45. How we do the background estimation? We use the control data sample. Like for example, here you can see the control data sample for the the K plus and π+π0, where we measure the fraction of π+π0 in the two signal region respect to the peak. We use this fraction, we multiply for the number of events that we see after the whole binary bar selection in the peak, and so we get the expectation of π+π0 in the signal region, region 1 and region 2. We use the same procedure for the K plus mu neutrino and for 3 pion. For the other background, we use the Monte Carlo simulation normalized to the single event sensitivity that was measured to be 1.11 plus minus 0.07 times to 10 to the minus 11. For the upstream background, that is the main background that we get. First, we can tell you that the upstream background is due to pion produced upstream of the fusion volume, or lithium decay, or interaction of the beam particle with the beam spectrometer material. The pion can be associated to the accidental particle of the beamline and dangerous if it's coupled with pion scattering the first spectrometer chamber. We use the cam-pion association and geometrical cut that we get that are effective on this background, and the geometrical origin. This event allows us to define a sample of background validation that was estimated with a data-driven model. You can see here the expectation of event of K plus in plus neutrino for the 2018 sample, 7.58. The total background of expected is 5.28 events. As you can see, the biggest background is due to the upstream background, 3.3. The background expectation are validated in control region using blend procedure. For example, here I can show you the control region for the main decay. You can see the control region for tripion, for pi plus pi 0, and for mu neutrino. You can see here that the event obtained after the unblind of the control region are in line with the expectation. For example, for the 2 pi plus pi 0 control region, you can see that in total we get 18 events, and we was expecting 18 events precisely. After the unblinding of the signal region, we get a total of 17 events respect to the 13 events expected. Together with the 17 events, we did a combined analysis, adding the event observed in the 2016 data and the 2 events observed in the 2017 data. Here is a plot integrating the full plus momentum of background and signal. You see that there is a good agreement between Monte Carlo and data, both for the background and the signal regions. And this is the result of the whole run 1, so from 2016 to 2018. We get 10 to 6 plus 4 minus 3.4 for the statistical error, plus minus 0.9 for the systematic error, times 10 to the minus 11. You can get that it is the best measurement obtained so far. You can see that all the experiments used to measure this decay always better before with the upper limit than the first measurement done by the experiment A787 and 949, and that this result means the best one. You can see even that the theoretical prediction was improved years after years. Here is a zoom, where you can see that our measurement is in agreement still with the theoretical prediction, and we plan to improve this resolution of the measurement in the next years. In summary, this is the result from the complete run 1 of NSC2. Observed 20 events in total. Expected background was just 7 events, so we get 10 to 6 times 10 minus 11 of branch ratio is the most precise measurement obtained so far, compatible with the standard model. And for the next run, we'll resume that taking a few months. Then we got a modification of beam line and installation of additional beam spectrometer station, Vetan counter, new calorimeter, and other detector to suppress the upstream background. That is the main background I will show you too. More information can be found in the NC2 addendum linked here. Then I speak about even lepton flavor and number violation counts decay. A violation of lepton number and lepton flavor conservation law is predicted by several Bian-Sadler models, like for example the neutrino Majorana and the leptoquark. There are previous experimental results. For example, these two results from the experiment E865 and NA48, and we improved that those experimental results. In NCSU, we used the 2017-2018 data with blind analysis and normalized with the standard model decay, like for example K plus, Pi plus, and 2 lepton, and K plus in 3 pion. The acceptance for this validating decay is 5% for that with 2 positron and 1 electron and 1 muon, and 10% for 2 muons. The main background are due to pion misidentification and bounded decay in flights. For example, here I show it decay plus, Pi minus, mu plus, mu plus. On the left is the standard model decay. In this peak, there is a decay plus, Pi plus, mu minus. On the right instead is the search of this bilateral decay. The dashed lines show the sigma region where we found one sigma, one candidate, sorry, and was one candidate expected even 0.9 plus minus 0.41. And this brought to the upper limit of 4.2 times 10 to the minus 11. The same is for the decay with 2 electron. On the left, the standard model one. On the right, the selection for the left number evaluation was expected 0.16 event. We found no candidate, and so we get 2.2 times 10 to the minus 10 of upper limit. Here I show you the result for the decay with 1 muon and 1 electron, with a upper limit of 4.2 and 6.6 times 10 to the minus 11, and the final the schema of all the result obtained so far. You can see that we got up now improvement of the upper limit with respect to the previous experiments. For example, improvement factor 2 using just the 2017 data for the K plus, Pi minus, and 2 positive muon. Factor 3 using just 2017 data for data with 2 electron. This can be improved using even 2018 data. Instead, for the decay with 1 muon, positive muon, positive electron, and 1 negative electron, and 1 positive muon, we get a respectively with an improvement of factor 12 and factor 8 using both the data sample. For the Pi plus, mu plus, A minus, we are not yet competitive with previous dedicated experiment. Instead, the preliminary analysis of the mu minus and 2 positron and A minus and 2 positive muon seems to be interesting. We get up now just with 2017 data interval sensitivity of respectively 1 to times to the minus 10, 5 times to the minus 11, and especially for the second one, there is no previous limit from previous experiments. Another interesting result is pi 0 in minus A plus, that will get an improvement of factor 11 using both data samples with respect to previous experiments. This is all from NCGO. Thank you.